Okay, so now we're recording again. Welcome to the first actual academic topic in this class. It's going to be measurement and estimation, which is actually not a physics topic at all, but it is a very useful skill that we will need, not just in this class, honestly, but in any science course, is how to quantify measurement and estimate things. So I mentioned to you earlier that I showed you a video about it's a British panel show. It's comedic, but anyway, there was a clip that I wanted you to see that is really applicable to what we're doing here with the measurement and estimation stuff. So I'm going to queue up that clip again. Hopefully I set it up correctly with the Zoom, and I want you to kind of pay attention to I don't know, the words that the host and the host's assistant are using here. Okay, so I'm going to see if I can cue that up. Let's see here. Okay, so I'll play you the clip and you can listen. Okay, so that was the clip, and I don't know if you caught that. It's a stupid game show, really. The exact task that they were doing is not of consequence here. I hope you listened to the banter, though, between the host and the host's assistant. Let me just share this again. There we go. He was saying how many donuts did, or what was the weight that this guy had, and the host assistant said 600 and something donuts, and the host had a funny face, like a perplexed face, and then turned and looked at his assistant and said, 600 and something donuts, that doesn't sound right. And then the assistant said, oh, grams, sorry. And then he's like, oh, grams. That is an example of why measurement is important. Now, of course, this is a stupid British television show, so the actual actions of these people are not of consequence, but I just watching the show, and I noticed that. I'm like, I'm going to be teaching about measurement on Monday, so I will show them that clip. So, and then later in that banter, you saw them, or you heard them talking about, grams, and then kgs, kilograms. So, we have this sort of notion of measurement, and maybe it's been formalized, maybe you've been officially taught measurement concepts, maybe you haven't, maybe it's just you've picked it up in the language that you've been raised with in day-to-day language. So let's just start our conversation with units. That's, I think, an appropriate way to start. So how tall is the CN Tower? Now, if we were actually in an in-person class, I would ask you to raise your hand and shout it out. I'm going to pretend I'm you for a second. If I ask you how big the CN Tower is, I can only imagine some of you guys saying, like 300 meters or a kilometer or, 100 meters or something like that. I'll tell you right off the bat, I don't actually know how tall the CN Tower is. And that's my point, is I can be a little bit cheeky and I can say, well, I could invent a new unit of measure, a new unit of length. I'm going to call it, let's see here, I got to make this smaller. How do I make this smaller? Is that going to be smaller? There we go. Okay, I can invent a new unit and call it CNT, which stands for CN Tower. And, oh, that's a problem. So new unit, and I'm going to call it CNT. I don't know why it erased itself, equals CN Tower. So I can actually definitively say with absolute certainty that the CN Tower is exactly 1 CN Tower tall. Now, seems like I'm cheating the system, but in fact, most units of measure are based on exactly things like that. America uses things like feet. Well, that's not just an affectionate name that sounds like the part of the body. It's the length of a foot is actually based on, at one point in time, how long a foot was. It was, that's where that standard of measure came from. So same things like a yard, or stuff like that. Like there are things in real life that these units are referencing. So, you know, for me to invent a new unit called CN tower, CNT, that's totally acceptable. Now, this is actually a nice segue into unit converting, because there's obviously more than one unit that we can measure distance with. You know, even in science alone, we have things like there's a fathom, there's a parsec, there's an astronomical unit, AU, there's a light year. Light year, by the way, is not a unit of time, even though it's got the word year in it. It's the distance light travels in 1 year, so it's actually a unit of distance. So these are all different units to measure distance, and obviously feet and inches and things if you're in the US. And there have to be a way to sort of compare the two. You know, a light year, 1 light year does not equal 1 CN tower, obviously. So there has to be a sort of a way to compare these two. So this is a nice segue into the subtopic of unit converting. Unit converting. And this is going to allow us to compare scales and values with each other. Okay, now that brings me to this point. What's the point of a unit? Well, it's to provide a scale. You know, I don't want to say that, you know, I think I weigh about 180 pounds last I checked. I don't want to say I weigh like, you know, 10 bajillion, you know, atoms worth of weight. That's just a huge number that I just gets your mouth all jumbly. Why would you do that? You choose the appropriate unit for the scale of number that you're talking about. So, you know, pound or kilogram, I guess, would be a reasonable unit to measure my weight. I'm 180 pounds. That's not a really big number to get your mouth all jumbly with. Same thing with money. You know, would you say you have $10? Probably. It's an easy unit to quantify, you know, $10. Would you say would you say $10 in the unit of cents? Probably not. It'd be an extremely large number. Why would you do that? Same thing with thousands of dollars. You know, if you had you know, $6,000 in the bank, well, don't we all wish that? If we had $6,000 in the bank, you know, you wouldn't quote that number in pennies. You know, that would be ridiculous. So units provide a scale, and that's really what I'm driving home here. And also the communication of the units with one another. We call these SI units. SI is actually the French wording, Standard International. I don't know why we use the French wording, but we have. English people would say standard units, or the international standard. It's a way in which we can communicate between different countries and scientists around the world for, you know, all of our calculations with ease. Now, most of us abide by this, other than the US. I don't know why. The US is just kind of like on a whole other, I don't know, kind of like another time zone, but another dimension, so to speak. You know, the rest of the world is using the metric system for their SI units, and America's gung-ho for the imperial system. So I don't know why. But anyway, we're going to be using SI units. And what SI units mean, what the SI unit means, SI units. So there's going to be 3 different types of measurement we're doing in this class. There's going to be time, which are going to be measured in seconds. That's the SI unit for time. And then there's going to be distance. And the SI unit for distance is going to be in meters. And then there's going to be mass. It's the other quantity we're trying to measure. And mass is going to be measured in kilograms. So these are what the SI units are for the standard quantities that we're measuring. So if you're an international student from the US, I apologize, but you're going to have to learn the metric system. Now, luckily, even in the US, you measure time with seconds. And mass, and unfortunately, if you're from America, you're going to have to learn kilograms. That might be a little bit foreign to you. Okay, let's just do an example right off the top. So if you're from America, this will be right up your alley, because that's what I'm actually going to convert between, pounds and kilograms. So let's say Bob happens to have a mass of 105 kilograms. What would the standard imperial weight scale display if Bob were to step on the weight scale? So standard imperial weight scale, the key word there is imperial. Imperial meaning the imperial system, as you would find in America. So pounds, this is really saying what is Bob's weight in pounds. Now, why they chose to annotate pounds with LBS, you know, for the silent L and B in pound, I don't know. I didn't invent the unit, I'm just using it. So to convert between these two, you actually just need the conversion factor. So you can look it up. These are one of these things that it's impossible to just know. You just kind of have to look it up. 1 kilogram happens to equal 2.2 pounds. So I'm going to box this in green for you guys. So what we're doing is we're starting with Bob's mass of 105 kilograms, and eventually we need to get his mass to something pounds. Now, we do this by multiplying by the conversion factor. So I'm going to multiply by something, and we have to cancel. I'm going to change my color here. We have to cancel the kilograms. So that means we put kilograms on the bottom and pounds on the top. This will allow us to, when we multiply, this will allow us to cancel the unit of kilogram. Now we just need to deal with the number, the converting number. So we need pounds on the top and kilograms on the bottom. So if we take our ratio here, we can rearrange this. So pounds on the top, kilograms on the bottom. We can say this is going to be 2.2 pounds per 1 kilogram. That's a point, not 22. 2.2 pounds per kilogram. I don't know why that period didn't, there we go. So that's what I'm going to write here, 2.2 kilograms per 2.2 pounds per 1 kilogram. And then when we multiply, we're going to get 105 times 2.2 pounds. And if you happen to have a calculator handy, you'd see that this is approximately 131 pounds. So that's just a very standard, very easy example of how you would convert units between, let's say, pounds and kilograms. So 2.2, I guess, is the number I'm going with there, 2.2. Now, I'm going to sort of foreshadow what we're going to talk about next with estimation. Let's say you didn't have a calculator handy. And just so you know, I didn't do that in my head. I did that ahead of time, having prepped for this lecture. So I know that, you know, that multiplication is 231. What if I didn't prep this ahead of time? What if I didn't have a calculator? Honestly, I hate calculators. They are my worst enemy. You know, you type in long equations, and you know, inevitably you either miss a bracket, or maybe the computer or the calculator you're using doesn't have brackets, so the calculation gets all jumbled. Terrible. I hate calculators. So what if I wanted to approximate this? I'm going to do this in green to show you it's a different calculation. If I wanted to approximate this, well, 105 is easy enough, 105. And 2.2, that's close enough to the number 2, okay? So I know in the back of my head, the answer should be around 105 times 2, which is about 210 pounds. Now, I made the 2.2 smaller, which means my answer of 210 pounds is an underestimate. So I know on the low end, my answer should be around 210, just a little bit bigger than 210. And that's a good way to just sort of sanity check. I'm going to write that down, sanity check your answer. So by all means, use a calculator if you want to, but you know, if you're anything like me, your calculator and you are going to have a love-hate relationship. So it's really good for you to be able to have these sort of critical thinking skills to sort of double check your calculations with your calculator, because I've lost so many marks by just, you know, blindly typing things into the calculator, writing them in on the test, and then, you know, the TA or the professor was marking it and probably scratching their head at the time. What is Mark thinking? Like, you know, there's no way that's orders of magnitude wrong, you know, blah, 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 blah. It's good to check your work. Don't lose silly marks to things like that. Here's another common example. Come on, I need to insert some space. Okay, there we go. So another common example is converting between kilometers per hour and meters per second. You know, when we're driving the car, we're used to speeds like in kilometers per hour. So we know when we're driving in city streets and neighborhoods, you know, your speed is about 40 kilometers per hour, maybe 50 kilometers per hour. But, you know, when you're walking, you know, either on the track or on the treadmill or even just taking a stroll outside, you wouldn't measure your own speed in kilometers per hour. You'd probably measure it in meters per second. So both of these are SI units. You know, kilometers is still a form of a meter, and seconds is the SI unit for time, but hours is a variant on that. So, you know, you can commonly switch back and forth. So let's do an example. If you're driving, and let's say you're driving at the appropriate speed. I speed a lot, but let's pretend you're a good driver, not like me, and you're traveling at exactly 100 kilometers per hour. And you want to know what that speed is in meters per second. So we need to eventually get to something meters per second. Now, what we can do is we can systematically multiply by conversions one at a time as needed. So I see a kilometer up top and a meter up top. So we need to convert kilometers to meters. So let's do that. We multiply by something, meters on the top, kilometers on the bottom. We need kilometers on the bottom because then we can cancel the kilometers. And we know kilo, this is why the metric system is superior. Yes, I'm using the word superior. Converting between powers of distance is literally just powers of 10. So kilo means 10 to the 3 or 1,000. So there are 1,000 meters in 1 kilometer. That's not true for inches and feet and yards. Don't even get me started on the imperial system. It makes no sense. So there's that. We've successfully converted to meters. So I'd say that aspect, we're done. Meters is done. However, we still have hours in the bottom, and we desire seconds in the bottom. So we got to convert that. So next up, we have hours on the bottom. So I'm going to put multiply something, hours on the top, and one step down from hours would be minutes. So for every 1 hour, there is 60 minutes. And we're not quite done because now we have, although the hours have canceled out, we now have minutes on the bottom, and we don't want minutes, we want seconds. So we have to further multiply by something, and we want minutes to cancel on the top and seconds to be on the bottom. So for every 1 minute, there is 60 seconds, and the minutes will cancel. And after all is said and done, the only thing that's left is seconds. So we have now dealt with the seconds. So how do we find our final answer? We just multiply all the numbers. So we have 100 times, what do we have here? We have 100 times 1,000 divided by 60 times 60. So 6 times 6 is 36. So 60 times 60 is 3,600. Now 1,000 over 3,600 is just 3.6 meters per second. So again, if you had a calculator, you could actually go ahead and calculate this precisely, and it's in and around 27.8 meters per second. Now, again, we can talk about estimation in a second, which we will. We can ballpark that answer if you don't have a calculator. The important thing I want you to take away, though, here is the ratio of 3.6. So if you're converting between kilometers per hour and meters per second, you should be thinking to yourself 3.6, 3.6, 3.6. That's the ratio. So if you're going from kilometers per hour to meters per second, you divide by 3.6. If you're going from meters per second to kilometers per hour, you multiply by 3.6. So just very quick kind of multiplication factors that I'm trying to present you with here. Same thing with kilograms and pounds. You know, if you have a kilogram, how many pounds do you have? You roughly multiply by 2. If you want an exact calculation, you multiply by 2.2. Now, one last example here. Well, actually, no, we'll do that a little bit later. Moving on to estimation. So as the meme implies, nobody has time to sit there and do exact calculations. Now, if you're a math major and you're taking my class, I apologize in advance. I'm probably going to be poking fun at you multiple times throughout the semester. Math people, trust me, I mean, my degree's in math and physics and computer science, so I know math people, I know the math world. They absolutely love their exact numbers. You know, you've been told by math teachers in high school, and if you've taken calculus in university, you know, they tell you always leave things as a fraction. If your number involves pi or e, just write pi or e. I don't know. They seem to love it. I don't know why. Physicists, we tend to be more pragmatic, down to earth. You know, having a number as a fraction doesn't tell us much. You know, if I want to know, you know, how much weight the bridge can hold, my answer can't be in terms of pi and e. I need to know an exact number. How many trucks can I fit on that bridge before it collapses? Give me an actual number. So we're all about the numbers. It's good to have formulas, don't get me wrong, but in terms of having time for precise calculator, you know, keeping things as fractions and then putting the fraction lowest, like reduced form, ain't nobody got time for that. So I'm gonna teach you some techniques to help approximate some numbers. Hopefully that makes your life here a little bit easier in this class, and hopefully in your day-to-day lives as well. So there's three types of estimations. There is an order of magnitude approximation, and this happens, what color am I on? There. So the order of magnitude calculation happens with large numbers. So we're not talking about things like my weight, you know, because order of magnitude is like numbers, powers of 10. So, you know, I probably, in terms of pounds, I have about 2 powers of 10. You know, I'm about 180 pounds. That's 2 powers of 10. But saying I'm 100 pounds, which is still 2 powers of 10, and 800 pounds, which is still 2 powers of 10, very different. I mean, if I'm 800 pounds versus, you know, 200 pounds, that's a very different, one's probably death and one is, you know, a reasonably healthy person. So I would not do an order of magnitude calculation when it comes to smaller numbers like weight, like my weight, for instance. So if you do an order of magnitude calculation, you're only concerning yourself with the powers of 10. You know, are we talking about like 1,000,000 kilograms, or are we talking about 1,000 kilograms? You know, in and around there. It's kind of like when you're calling, you know, for a quote on, you know, internet or something like that. You know, are you going to be charged, you know, tens of dollars or hundreds of dollars? You know, is your cell phone, you know, let's say unlimited talk, unlimited data, are you going to be paying $200, or are you going to be paying like a couple of tens of dollars, like $50 or $60? You know, you don't care about the exact number, whether it be like 57.50 versus like 50. You know, you just care about how many $10 bills are involved, you know. Next up, the other kind of approximation is called ballpark approximation. So a ballpark approximation is kind of the other examples that I've been giving when you have smaller values. And, you know, the power of 10 is important, but so is the sort of number. So the power of 10 is important, but so is the value. So both, you know, like if I say, you know, I'm 180 pounds, that's 2 powers of 10, but it's also like it's 1.8 times 10 to the 2. That's very different than saying I'm 8 times 10 to the 2. Both same power of 10, same 2 powers of 10, but a different actual value as well. So a ballpark approximation also considers the value. And then a math approximation, this happens when we have to approximate values that do not exist. So an example of this might be like, you know, how many cars are there in the city of Mississauga? Is that number sitting somewhere on a database? Maybe. I don't know. But, you know, you can approximate that. You know, you can make some reasonable assumptions, you know, and there's so many different ways you can approach this. You know, you can say, you know, how many schools are in the region? Well, each school has, you know, X amount of families districted to that school. So if there are 10 schools, then that means there's so many families. Let's say each family has one car. Like, you're inventing numbers here, reasonable numbers, but you're inventing numbers nonetheless. So that's another type of estimation. It's not an exact estimation. It's kind of like a hand-wavy estimation. So let's start with the first one. Estimate the number of seconds in a year. This is not a math estimation. We have concrete numbers for this. So if, you know, here we can actually just do it. We want number of seconds in a year. Well, this is reasonably easy to calculate. We can say that there are 3,600 seconds in 1 hour. We know this because we just did that question, you know, converting between kilometers per hour and meters per second. So we know that 3,600 thing existed. Now, that's if we only have 1 hour of time. How many hours are there in a year? I don't know. But how many hours are there in a day? That I do know. So I can multiply by 24 hours in a day. So hours there cancels. And day is not what I'm interested in. So what's the next ratio that I know? Well, yeah, there's week, there's month, but I happen to know how many days there are in a year. There's 365.25. This year was a leap year, by the way. So we can't forget that 0.25 because it matters. And that's how many days there are in a year. So we kind of cross out the days. And then what's left is we're going to get 3,600 multiplied by 24 multiplied by 365.25 seconds per year. Oh, that's a terrible year. My apologies. Year. Okay. Now, if I had a calculator, no problem. I could just plug this into the calculator. The whole point, though, is I don't have a calculator. So how can I sort of estimate a number and not sound like a complete idiot when talking to people? You know, I want to communicate to the world that I have some level of numeracy skills and some number literacy. So let's just kind of approximate things. Let's round everything to a number that I know how to manipulate. So let's call this round to the nearest, you know, whole power of 10. So 3,600, let's say 4,000. Okay, this is approximately equal to 4,000. 24, I don't know how to multiply by 24 off the top of my head. Let's round that to 20. 365.25. Closest power of 10, or sorry, closest multiple of 10, I guess would be, well, not multiple, like whole number, I guess, or not whole number, but you know what I mean. 400 would be the closest one that I can easily do without a calculator. So I'm just gonna eat up some space here. There we go. So, equals, now 4,000 is gonna be 4 times 10 cubed. 20 is 2 times 10 to the 1. And 400 is 4 times 10 squared. 4 times 4 is 16. And, oh, well, actually, let's just do it. 16 times 2 is 32. Times 10 to the, let's see here, 10 to the 3. So 10 to the 3 times 10 to the 1. So we've got 4 10s and then 2 more 10s. So that's going to be 10 to the 6. And then 32, let's put this into scientific notation. So 3.2 times 10 to the 7 seconds. And again, we've approximated up until now. That 3.2, let's just get rid of the 0.2 and just say 3 times 10 to the 7 seconds. So there you go. Without a calculator, I've just approximated the answer to be 3 times 10 to the 7 seconds. Now, if you actually had a calculator, and maybe half of you have done this already, I'm not sure, maybe you're ahead of me on this, but if you actually do just take a calculator and calculate it, the real number, if you're curious, is 3.156 times 10 to the 7 seconds per year. So this number alone would even be rounded to 3.2. So oddly, you'd actually get the correct answer if you left the 3.2, and we obtained that by approximating. I never even used a calculator. So it's oddly a powerful method to do that. We are running out of time a little bit, so I'm going to skip example 5. You'll notice here that it's actually a copy and paste from something. It's actually a copy and paste from that typed PDF lecture notes that I told you that there is. So it's not the PowerPoint slides, it's the other one. It's example 5 and the other one. So the solution is there for you if you'd like to look at it. And for those of you who have found the G.N. Coley book, the PDF of it, there are so many more examples in chapter 1.7 for you. Now, there is one other thing I want to review with you before we go on to something more complicated. A lot of you have been emailing me about the pre-class quiz, all concerned. So, you know, maybe you got one wrong on it. I just kind of want to explain to you how much time you put into drafting that email and being concerned and stressed about 1 mark versus the reward you might get if that 1 mark was awarded back to you. So let's actually calculate or estimate how much 1 question will change final grade. Now, I don't know offhand how many questions there are, but on the first pre-class quiz, I think there were, 6 questions? Let's go conservative. Let's assume there are 5 questions, okay? So let's say there are 5 questions per pre-class quiz, okay? And for the post-quiz, let's assume, I think there's more than 5, but let's just assume there are 5. Oh, sorry, before we do that, let's say there's 3 lectures per week. So there's going to be 15 questions, pre-class questions total per week. Plus, and let's say there are 5 questions on the post-class quiz. So we're looking at around 20 questions per week, or 20 marks, I should say, per week. And there are 6 weeks total in the class. So altogether, there's going to be about 120 questions, or 120 marks, I should say, that you can get as a collective sum from the pre and post quiz questions. Now, all of these are only worth 5% of your final grade. So if you're talking about getting 1 question wrong, then really you're saying, what is 1 out of 120? Well, that's a bad 0, sorry. What's 1 out of 120 times 5%? Because that's the maximum quota. Well, again, without a calculator, because I'm just kind of spitballing here, I'm going to start changing these things to things that I know. So, you know, you can change this. Now, if you know what 5 over 120 is, go nuts. You know, it's a reasonably easy calculation, but let me show you how to implement the previous concept. So let's round 120 down to 100, because that's something that I easily know. And 5 is easy enough. So 5 over 100 is 1 over 20, which is 0.05. So percent. That's 2 decimal places. So when you get 1 question wrong on, and this is on the high end, you know, I actually think most of the pre-class has like 6 questions, and I think the post-class quizzes actually have more than 5 questions on them. So like this denominator of 120, I'm underestimating. Like that denominator should be a lot bigger. So on the high end, 1 question on a pre-class is only 0.05% of your final grade, quite small. So you'd have to nickel and dime me constantly throughout the entire semester to even have a chance at having that matter in any way. Because when we upload grades to Acorn, we upload whole numbers. You can't upload decimal numbers to Acorn. So, you know, 1 question is 100 times smaller than what we upload to Acorn. So hopefully this kind of reinforces that, you know, the grades on the pre and post class quizzes are really not that important. it's to get you involved in the class and to make sure that you're kind of following along. It's not me trying to mark you wrong. And it's not that I don't want to give you marks where you deserve them. It's just, it's really not worth anyone's time to nickel and dime each other. Like, you know, you're going to spend so much time drafting emails on these things. Just, your time is better spent doing some more homework and making sure you nail the midterm and the exam. And that time could be better spent then. Okay, we are running out a little bit of time. There's an example which I'll skip, but the full solution of the example is provided in those typed lecture notes that I've given you. I believe it's example 7 in the measurement and estimation.pdf file. I'll just outline it for you briefly though. How many piano tuners are there in New York? This is a great question. This is an example of a question where you have to sort of make some reasonable assumptions. How many people are there in New York? That's something you can Google. How many of them have pianos? There's no answer to that. Make a reasonable number. Do you have a piano? Out of everyone you know, how many people do you know have a piano? Let that guide you. You know, me personally, I would say about maybe 30% of the people I know have a piano in their house. You know, that number might be different for you. So there's no one correct answer for this. These are, you know, some reasonable assumptions you've got to make. So please, I would encourage you in your, you know, after the lecture, please review those typed notes and kind of go through the solution there. Here's a sort of funny comic I found online about unit converting in conjunction with estimating. Not that hopefully don't do this, but you know, it's a funny comic on these sort of principles. Is, you know, if you went outside and laid down on your front lawn with your mouth open, how long would you have to lay there for a bird to poop in your mouth? And you know, this is an exercise in both units, converting units, as well as approximating. So you can see here, period is 1 over frequency. They're estimating there's about, you know, 3 billion birds on the planet, and they're dividing by the surface area. You know, they're working their way to time, and they're approximating the surface area of their mouth. So they're pretty much ballparking. You'd have to sit on your lawn for about 200 years before a bird poops right in your mouth. So I don't know, kind of funny example of both unit converting and stuff like that. Although tell that to my car. You know, I wash my car, I wash all the bird poop off my car, and every time I go back, there seems to be more. So I don't know, maybe there's a different approximation for cars. Okay, so just a brief summary. You know, if you're doing some estimating, round your numbers to nice, easy round numbers. You know, don't make your life hard. If needed, make some reasonable assumptions. And the word reasonable there is in quotes because, you know, don't be making unreasonable assumptions. Like, you know, if you're trying to approximate how many people live in Mississauga, you know, don't just wildly guess like 4 million people. You know, that for one, you could probably just Google how many people are in Mississauga. That's something you can fact check. But I mean, you also want to make something reasonable. Also, when it comes to like pianos, you know, if you want to ballpark how many families have pianos, you know, it is unlikely that like 80 or 90% of the people or households have a piano. You know, so like reasonable assumptions. There's no correct answer, but there's definitely wrong answers. And I guess that's my third point. Yes, we know it's not the correct answer. We're not mathematicians. You know, we're not here to like, you know, quibble over pi being 3 or pi being 3.14 or 159. It's meant to just be a sort of quick way to double check kind of roughly what the answer is going to be. Okay, I've also included the publisher's PowerPoint slides. The publisher meaning the Gian Coley book, who publishes the book. For some reason, I have access to them. It came with the book. I don't know. I posted them there for you guys. I see no reason why I should just keep them to myself. But, you know, I'm not going to teach with them. I've obviously made my own slides. But every batch of slides will have them at the end for you. So they're there if you want to look at them. I don't know if they're going to provide more information or not, but they're there for you. Okay, I'm going to quickly look at the chat. Where's my chat window? There's my chat window. Okay, I'm going to quickly look at the chat. Hopefully Oksana's been dealing or answering with some of your questions. I'm going to open it up now. If you have any questions, for me about what I've just talked about, go nuts. We don't have a lot, maybe 2 minutes. We have about 2 minutes that I can spend on this. In which situation can we use the approximation? Well, I mean, there's no rules. I mean, the inherent nature of estimation and approximation is we aren't doing the right answer anyway. In fact, we are specifically not going with the mathematically correct answer. So once you start going into approximating in the realm of approximations, you know, just there's some guidelines for you to follow, but there's no kind of hard and fast rule. You know, like I rounded 3,600 to 4,000. You know, so just use your best judgment. Do some practice. There's some practice in the textbook as well to help guide you. But you know, hopefully with practice that'll become clearer. Would we receive conversion sheets or formula sheets in the midterm quizzes and finals? Normally I would provide formula sheets, but to be completely honest, now that the class is online, I mean, you could just Google any conversion you need. I mean, how am I going to monitor that? So I may as well embrace it. You know, I mean, it would be stupid of me to just say, don't use Google during the test. I mean, I'm still going to say that. Don't get me wrong. Officially, I will absolutely say that. But obviously, nothing stops you from just Googling what's the conversion between pounds and kilograms. You know, so I don't think I'm going to provide a formula sheet this year for those conversion things. Maybe for the formulas, just to make them accessible for you. But little tidbits like that, you could probably just Google. I've heard from previous students that the midterm exams are very hard. Would it be harder this year because it's online? Well, I don't know who you're talking to in the past. I mean, there's always going to be a batch of students who think things are hard, no matter how easy they are. I think the tests in the past have been, you know, fair. They're not. I don't think they're hard. In fact, most students, when I post the solutions, they're not overly involved. I mean, most students would agree after I post the solutions, it was a very fair test. If they didn't do well, it's probably because they weren't prepared. Am I going to make the test super, super hard now that it's online? No. I mean, that's not the point of any of this, right? The point of this is to make sure you guys are learning. I'm not here to overly punish you guys. So no, it's not going to be harder just because it's online. Do we have to use this kind of estimation on the test or exam? Look at the past tests and exams. When I post them, you'll see. So for the solution on the midterm, are they approximate value? Again, you'll see when I post them, you'll see. I was just wondering, in order to read the chapters in the book, I just look up the topic we were reviewing. Yeah. Well, there's no reading schedule in the syllabus because you just follow along with the lectures. You attend the lectures and you see what we're talking about. So yeah, today we talked about measurement and estimation. Go to the textbook and read up on a chapter on measurement and estimation. Whatever book you're using, whether it be the G. N. Coley book or otherwise, all of them have one. To know which textbook chapters to study, do we just go by name? I mean, use your brain. We talked about measurement and estimation. So a different book may not call it measurement and estimation, but whatever title they use in that other book, I'm sure is going to be very similar to measurement and estimation. Will we be getting an answer key for Pat? Yeah, I'll post the solutions for them, so don't worry. Okay, we have to move on before we run out of time. So hopefully Oksana can deal with the other questions that come by. I'm going to stop the recording now and then restart it again because we're starting a new topic. So just bear with me on that one a little bit. Where is it?